8M7L8, the long division algorithm. We continue on with converting fractions into decimals and understanding when decimals or when fractions will terminate when written as decimals. We're also going to give you a little special homework help here on lesson 8 because they ask you a few kind of questions to test your knowledge about the when fractions will terminate and when actually numbers that are written as decimals can be converted back into fractions. So we're going to talk a little bit about that, looking at a decimal and knowing whether you can convert it into a fraction or not, because it's not always obvious what a repeating pattern is. So we're going to give you some homework help on that as well. So let's get on with it and get over to our Sketchpad. And let's talk about our lesson goals here. Again, using long division to convert fractions to decimals. Now, I think that this is something you've learned before, but we're going to repeat it again today. If you know how to do this, you can skip past some of the examples that we'll be doing today. But I encourage you to at least go to the homework help, which will be the couple slides past the long division examples, because that'll really test your knowledge of whether you really understood the essence of the entire lesson. The second thing we're going to do is we're going to recognize the difference, and this is what we're going to do a little bit on those last couple slides, is recognizing the difference between patterns and repeating patterns in decimal numbers, and then what that means, okay? So we'll talk more about that as we get into those slides. Now, one thing I want you to recall, this is something from an earlier lesson in this unit, that any number that is written as a fraction, right? So A over B, like, 7 over 9, or, 123 over 7. Any number that can be written as a fraction will either terminate or have a repeating pattern when written as a decimal. So an example of termination is 1.25. That number terminates. And then a repeating pattern would be a number like 3.33333, where we have this bar notation. So remember the bar notation that says repeat forever. And so that's a repeating pattern. Now, we know that numbers, and then we further learned in that lesson that numbers will terminate if the denominator has prime factors of only 2 and 5. So, for example, a number that's written as 3 over 25, this will terminate because the denominator b has factors of only 2 or 5. Doesn't have to have a 2 and a 5, it just has to have only 2s and 5s. We know that fractions will have a repeating pattern if the denominator has a prime factor other than 5. So like, how about 2 over 35? We know that will have a repeating pattern because 35, the prime factors are 5 and 7. Well, 7 is not a 2 or a 5, so that it will have a repeating pattern. Okay, so that's what we learned in an earlier lesson. I'm just recalling it for you here because it will kind of come into play as we talk further about long division. So let's look at this. So now, I usually go with teaching you how the book teaches you how to do a long division or how to do any lesson. But I just find this a little bit cumbersome and just kind of difficult. So you have example here where they show you how to convert 142 over 11 into a whole part and a fractional part, and you do kind of this crazy stuff where you say, well, 142 is equal, you try and find the biggest number that divides into 142 that can be multiplied by the denominator, and then you find this other number over here, 10. But the way you have to do it is you have to say, well, what's 142 divided by 11? And then you end up with, a 1, 11, 32. 11 into 32 doesn't go 3, it goes 2 times. So then you put this 12 here, and then you have your 2 times 11, 22. You have your remainder of 10, and so you put your 10 here, and then you put, well, 12 over 11, 10, and then you divide both sides by 11, and then you say, well, this is still 12 times 11 plus 10 over 11, and then you have this part here, we cancel the 11s, and you get a 12 here, and you take your 10 and you put it here. And so 142 over 11 is equal to 12 and 10 11s. Well, that's all nice and good, but it really kind of, I find this cumbersome. I find it cumbersome. Really, all you needed to do was this long division piece, and then you get your answer, right? You get your answer of 142 divided by 11 is equal to 12 with a remainder of 10, which can just be written as 12 and 10 11ths. I think they're trying to make something clear here, but I find this confusing. So anyway, so the process of long division, just, what we're going to do is we're going to find the integer part, and then we're going to calculate the decimal part all at once. Okay, now I think you know how to do this method here, but let's do 4 examples. If you know how to do it, just skip past this next slide. If you don't know how to do it, watch closely, and we'll just kind of go through it. Okay, let's move along. So here's my 4 examples. Now, the first thing we're going to do is we're going to look, and we're just going to see whether they terminate or repeat forever. That's the first thing, and then we're going to do our calculation, our convert. Well, we'll call it the conversion. Okay, we'll do it in blue. Okay, so this number here, the question is this going to terminate or repeat forever? Well, let's look. If we only have 2's and 5's in our prime factorization of the denominator, it will terminate. Well, 9 is 3 times 3, so this will repeat forever. Okay, this one here is a 3, so this is only a, that's its own prime factorization, so this one will repeat forever. 11 is just the prime factorization is 11, so this will repeat forever. And 8 is 4 times 2, 2, 2. So it only has 2's and 5's. In fact, it only has 2's, so this will terminate. Okay, so now we've done that little piece of work. So now let's do our long division. So remember box top. And I showed this in an earlier lesson. So is this 14 divided by 9, or is this 9 divided by 14? Kids get this confused all the time. Which is which, and the answer is box top. So this is our top, and so it goes in the box. If you think of this symbol here, it's kind of the box. The box tops. So it's not this one. So it looks like that. Okay, well, let's just erase all that. We'll leave our box top there. So we're going to put our 14 in the box and our 9 outside. So now when we do our long division, we put our decimal point here and our decimal point here. And we're just going to do our 9 into our 14, and that's a 1. And so this is our integer portion. And we put our 9 here, and we put our 5 down here. Now we could say the answer is 1 with a remainder of 5, but we want to turn it into, and that would be a fine answer, but that's not, or you could say 1 and 5 ninths. Both of those are fine answers, but neither one of those converts it into a decimal. And so we are looking in this examples as, convert to decimal. So we can't stop here. So let's just get rid of those guys. And let's do our continue with our division. So now we have to, we're going to put some zeros out here. Let's drop our 0 down. So 9 goes into 50. 6 times, nope, it goes in 5 times. 5 times 9 is 45. And we subtract down and we get 5 and we get a 50. 9 into 50 goes 5 times. And what we can see is we look like we have a repeating pattern, but we know we have a repeating pattern because we get a 50 here and then we see another 50 here. And so we know that it's going to repeat because, in fact, we can test it and keep going. And because we keep getting this same number here, we're going to keep getting the same number up here. And so now we get 1.5 dot, 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 which can be written as 1.5 with a bar. Okay? And so we did correctly get a repeat forever answer, which we predicted because we didn't have just 2s and 5s for our denominator. And here's our repeating forever pattern, 5. Okay, so let's go on to the next example. 124 divided by 3. Now, box top box. The top goes in the box. Okay, let's put our decimals down. 4, 12, 0, 4, 1, 3, 3, 1. So 41, this is our integer portion. And now let's put our zeros out, drop down our 0. Okay, 3 times 9, 3 is 9, 1, 0. Oh, do we see a repeating pattern? Well, I see these two numbers. And so I can expect on top a repeating pattern. Yeah. And so my answer is 41.3. Repeat. And we knew it would repeat forever. We predicted that. Let's switch colors on these guys so we don't get totally confused as we run into these other examples. Box top, repeat forever. Okay, 111. Put our decimals down. Put some extra zeros out here. 11 goes into 10, no times. 11 goes into 100, 9 times. 9 times 11 is 99. 1. This is our integer portion. 1, 0. 11 goes into 10, 0 times. 0 times is 0. Drop down our 100. 11 goes into 100, 9 times. 9 times 11, 99. 1. Put some more zeros out here. Drop down our 0. 11, 0. 0 times 11 is 0. 100. 11 goes into 100 9 times. All right, looks like we got a repeating pattern up here. And because we've repeated our number here, and we repeated this number here, this we can know confidently that this will repeat forever. And we know here that we expect a repeating pattern forever. So our answer is 9.09. Repeat. Okay. All right, 5/8. Box top. This will terminate, which is kind of cool. So let's put our 5 here. Box top. Top. Box. 8. 8 goes into 5 0 times. So that's a 0. 0 times 8, 0. 50. 8 goes into 5 6 times. Yeah, sorry, 8 goes into 50 6 times. 6, 48. 2, carry 0. Put a few extra zeros out here. 8 goes into 22 times. 2 times 5, 2 times 8. 2 times 8, 16. 40, 0. 8 goes into 40. Exactly 5 times, so we're done. 0.625. And we knew that it would terminate because it had only 2's and 5's, in fact, only 2's in the prime factorization of the denominator. So hopefully you can do all these examples, and you can do other more complicated examples. Again, any number that can be written as a fraction with it's a ratio of two integers will always repeat or terminate, and you know how to figure that out. Some numbers might take a while before they repeat. I'll give you a hint, like 1/13. A number like this will repeat, but it will take a long time before it repeats. So if you have a number like this, it will eventually repeat. So stick with it. All right, let's look at two other key pieces. And these, I'm going to put this, call this homework help, because it is. You got some examples like this on your homework. Now, the converse, and now this is kind of key in the lesson. The converse of an earlier rule that we learned is true also. So if a decimal, so we learned that if you write it as A over B, where A and B are integers, then it will terminate or repeat forever, right? If it's an A over B, and these are both integers. The other key piece is if a decimal terminates or it has a repeating pattern, it can be written as a fraction A over B. So again, if it, 0.3 with the bar over it, I know can be written as a fraction A over B because it has a repeating pattern of digits. So what is a repeating decimal? Now they're going to try to trick you in some of the homework, or maybe not trick you, but really make sure you understand what a repeating pattern is with their examples. So let's look at these examples. I give you 4 examples here, and you got to figure out which of these are repeating patterns. Repeating patterns that. So let's just figure out the rule. Let's just find the piece. I want you to pause and find the repeat. Pause and find the pattern in A through D. Just find the pattern, and then we're going to talk about whether that pattern is one that's a repeating pattern that will be able to tell you that that decimal converts to a fraction. Okay, so now I assume you're back. So let's see. So this says 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have this piece and this piece and then this piece. So what I have is 9. These are exact copies. These are exact copy. This is an exact copy. So this can be written as 0.1, 2, 3, 4, 5, 6, 7, 8, 9 with a bar over it. So because I can write it that way with a bar, I can use bar notation. Because I can use bar notation, this can be written as A over B. We're not going to do it, but this is a yes. This can be written in bar notation. Okay, that's what we're looking for. So let's look at this one. All right, well, here I have a 1, and then a 0, 1, and then a 0, 0, 1, and then a 3 zeros and a 1, and then 4 zeros and a 1. So the question is this is a pattern, because I know what's next is 5 zeros and then a 1. So it's 0, 2, 3, 4, 5, and a 1, and then 6 zeros and a 1. There is a pattern. There is a pattern, but not an exact repeating pattern. Because the pattern must have the same number of digits. So this is no. This is not a repeating pattern. This is not a repeating pattern that can be written in bar notation. You can't write, because how would you try to write this? You would, you can't write 0 point. It's not like that. And it's not like that. You can't write this in bar notation. So no, this is not a repeating pattern. This cannot be written as a over b fraction where a and b are integers. Well, let's look at this one. This one has a 1, 2, then a 1, 1, 2, 2, then a 1, 1, 1, 2, 2, 2, then a 1, 1, 1, 1, 1, 2, 2, 2. So this one, again, same rationale. Cannot be written as bar notation. So no. Cannot be written as a fraction. How about this one? 1, 1, 2, 2. 1, 1, 2, 2. 1, 1, 2, 2. This looks pretty good. We can write this as 0.1122 repeating. Right? Got the same length in each chunk and same numbers in each chunk. So this can be written in bar notation. So this one is a yes. This can be written as a over b. We're not going to do the conversion in this lesson. But it can be written as a fraction. Okay, now the final piece is, you're going to have some questions along these lines. And the question is which of these fractions will either terminate or repeat forever? Now remember, to terminate or repeat forever, it must be able to be written as a over b, where a and b are both integers. Well, none of these examples are written with a and b are both integers, but can it be rewritten as an a over b, where a and b are both integers? And the answer is, I want you to pause and try. And what I want you to do is I want you to simplify to a over b. And then C. See if they can be written as fractions where a and b are both integers. So I assume you're back, and if you didn't understand the instruction, then you probably didn't understand the homework either. But let me show you what I mean. So this can be written as 2 times pi over 43 times pi times pi. Now we can eliminate the pi's, cancel top and bottom, and we get 2 over 43. So we know that this is written as the ratio of 2 integers. So this is yes. This will, and this one will repeat forever. Yes. Because 43 cannot be written as, the prime factorization is 43. This is our prime factors. So it's not just a 2's and 5's, so we know it'll repeat forever. Okay, so let's look at this one. Well, this one is 2 decimal numbers, but if we look at what happens if we multiply both top and bottom by 10, which is a legitimate thing to do, another name for 1, 10 over 10, we get 2 over 9. So this is yes. We have the ratio of 2 integers, so it will repeat forever. Why will it repeat forever? Because it's got this 9 down here, which is 3 times 3. It's not just 2s and 5s. Okay, let's look at this last one. Well, it looks like A actually could be written as the sum of, or the product or the ratio of 2 integers. So let's see if this one can. 4 times pi over 11 times pi times pi. Well, we can cancel this pi and this pi, but we end up with 4 over 11 times pi. Well, that's as simple as it gets, and this is not an integer. So no, will not terminate or repeat forever. So this number, so I can tell you that this will never terminate, and it will continue forever without a pattern when written as a decimal. We don't prove that. I'm not here to prove that to you, but by rule, this rule tells us that this is going to be true. I'm not going to prove why it's true. So hopefully this was helpful. Hopefully at least these last 2 slides were helpful for you in working on your homework. We will get back to you with lesson 9 very quickly, and hopefully this lesson was useful for you, and hopefully you enjoy these videos. And if you do, I encourage you to like the videos, and I encourage you to subscribe to them, because it helps me know that people are watching and people care, and you're getting something out of these videos. If you really want something different, or some different help, more homework help, more examples, something that I do that you don't like, let me know. I'm here to help, and I really want these videos to be useful for you 7th, 8th, 9th graders, whoever happen to be taking this class. We'll see you next time with lesson 9.